let's recall that we were able to interpret sine, cosine, and tan in terms of right-angled triangles if the angle was restricted to the open interval 0 to pi over 2. So recall the following. So recall for theta strictly between pi over 2 and 0. Well, if you're in that range, there's a right-angled triangle which has internal angle theta. And we can label the edges as always. This is the adjacent side, this is the opposite side, and this is the hypotenuse. So if this is the case, we can interpret cosine, sine, and tan as ratios of appropriate things. So for example, cosine of theta is equal to the adjacent divided by hypotenuse. Sine of theta is equal to the opposite divided by hypotenuse. And of course, tan of theta, which is sine divided by cos, is the opposite divided by the adjacent. So I'd imagine this is how you first saw sine, cosine, and tan if you've been introduced to them. It's too restrictive for our purposes, really, because theta, we know, can take any value whatsoever for sine and cosine. And that's because the proper interpretation of sine and cosine is, well, the coordinates of your position on the unit circle given by the angle theta. But if you are between 0 and pi over 2, then you can interpret them in this manner. Now, the reason I'm doing this is because it's actually going to give us some pretty important special values of these trigonometric functions. So, as I recall, many people, when they talk about special values of trigonometric functions, they always bring up the idea of the unit circle. And when they say the unit circle, what they always seem to mean is just some evil diagram where you have a circle and all of these radial lines at different angles and lots of different kind of numbers, coordinates, root 3, all sorts of evil stuff. So often when you talk about the unit circle, when people talk about the unit circle in my calculus classes, they talk about memorizing that evil picture. That's madness. Do not memorize something like that. It's completely pointless. Number one, it hides what's going on, really. It's much more useful to actually understand why specific values are the way they are, because it'll make it much easier to remember them. So what I want to do is to look at how I could use this interpretation to determine sine, cos, and tan of three angles: pi over 4, pi over 3, and pi over 6. So here are some important examples. So I've just told you them, but let's write it down. Important examples. So forget this madness about memorizing some crazy unit circle picture with all sorts of radial things. No, we're not in high school anymore. We want to understand what's going on. So let's think about theta is equal to pi over 4. So imagine I take a right-angled triangle with internal angle pi over 4. What does that have to look like? Well, if the internal angle is pi over 4 here, so let's get this right, and this is a right angle, that's pi over 2, that forces the other side to be pi over 4, doesn't it? The sum of the internal angles of a triangle is 180 degrees, or pi in radians. So here's a really neat thing we can do. Okay, so we know, so remember what we're trying to work out. We want to know sine, cos, and tan for pi over 4. So if I've got exactly the same angle there and there, I know that I have to have exactly the same length here and here. So just for simplicity, let's just choose 1 here and 1. All right? So we'll choose 1 here and 1. And what does that mean? Well, because it's a right-angled triangle, I can apply Pythagoras. So if I apply Pythagoras, that means this side has to be the square root of 1 squared plus 1 squared. That's the square root of 2. That's the square root of 2. So again, let's just make sure we're fully on board here. Pythagoras says that the opposite squared plus the adjacent squared is equal to the hypotenuse squared. 1 squared, 1 squared plus 1 squared, and I only chose 1 for simplicity, is equal to h squared. That implies h squared is equal to 2. That implies h is equal to the square root of 2. Okay, now with this triangle, I can instantly read off cosine, sine, and tan just by doing the appropriate ratios. So this would tell me that cosine of pi over 4 is 1 over root 2. And that's also equal to sine, right? So it's the opposite's the same, isn't it? Now again, something that people always tell me from high school. They say, you can't write it as 1 over root 2. You can't write a radical in the denominator. Why not? It's correct. That is the number. You could multiply the top and bottom by root 2, and that would give it as root 2 divided by 2, but why would we bother, right? This is the answer. Next, tan. Well, that is the opposite divided by the adjacent. That's 1 over 1. That's 1. Awesome. So rather than memorize some madness on a unit circle, I know why these values are correct. I know why they are what they are, and it's because of this triangle. So this right angle triangle, I think, is pretty easy to remember. Whenever I'm confronted with this business about what's the value of cos of pi over 4, I don't remember it's 1 over root 2, but I do remember the right angle triangle. And then I write this right angle triangle down, and I take my time to go through exactly what you see here. And the more you've done it, the faster you are at it. Okay? So, what about your other angles? Pi over 3 and pi over 6. Those are interesting ones. So let's do pi over 3, or indeed pi over 6. So can I come up with a nice geometric way of getting these? Well, let's remember, again, the sum of the internal angles of a triangle is pi. So that means if I was to take an equilateral triangle, and here's one I've already done. So this is an equilateral triangle. So if this is an equilateral triangle, all the internal angles are the same. So in particular, up here, this internal angle would be, so let's make it a little bit smaller, would be pi over 3. Wouldn't it, right? So that would be pi over 3. So again, let me just make sure we understand what's going on here. So this is an equilateral triangle. Equilateral triangle. So all the edges are the same length and all the internal angles are the same. And as I said, all the internal angles are pi over 3. So this is not a right angle triangle. So it's not a right angle triangle. That's a bit of a pain, isn't it? But let's do something pretty clever. Let's cut it in half. So let's cut straight across like this with a right angle there. Now that is a right angle triangle. And if I've cut it in half, what do I know? Well, I also know that this angle here has to be half of pi over 3, which is pi over 6. All right? Now, it's an equilateral triangle, so let's choose for simplicity. So there are several ways to do this, but let's just choose that one and that one. So this is 2 and 2. I'm only doing this just to make the numbers add up nicely. So now, I've almost got everything I need, but I need to know what that length is there if I'm going to be working out cosine, sine, and tan. So that is just going to be Pythagoras. This length is going to be equal to square root of 2 squared minus 1 squared. So it's going to be the square root of 3. So again, let me just reiterate why this is the case. By Pythagoras states that, well, if I square this and I add 1 squared, it's going to be equal to 2 squared. Tick. So when I'm thinking about determining the values of sine and cos for pi over 3 and pi over 6, I think of an equilateral triangle. That's the first thing that goes through my mind. And then I say to myself, okay, what do I need to fill in? I go through the procedure I've just described. So no memorization of any kind of weird circle. I think about an equilateral triangle. So what can I see? Well, now it's a bit more of a mess, but let's kind of go through, let's do cos, for example, of pi over 3. Cos of pi over 3 would be the adjacent divided by the hypotenuse, so that's going to be equal to a half. And notice, if I was doing sine of pi over 6, then it would be the opposite divided by the adjacent, so this is also equal to sine of pi over 6. Neat. Well, if I was to do cos of pi over 6 now, what's this equal to? Cos of pi over 6 would be the adjacent divided by the hypotenuse, so that's going to be root 3 over 2. So this is what I said before when I was talking about unit circle memorization and weird root 3s. Don't want to be memorizing that. You should understand the process that goes into it. So root 3 over 2. And this again, if I was thinking about sine of 3 over 4, that would be opposite divided by adjacent. So this is the same as the sine of, pi over 3, not 3 over 4. So this is sine of pi over 3. And then what about tangent of each of them? Well, tangent of pi over 3 is equal to, so tangent of pi over 3 would be equal to, so that's pi over 3, the opposite divided by the adjacent, root 3 over 1. So this is equal to root 3. Root 3 divided by 1. And then I suppose finally tangent of pi over 6. Well, that would be what? That would be pi over 6 here. Opposite divided by adjacent, 1 over root 3. And no problems with having a 1 or a radical in the denominator. Why would there be? Lovely. So what I've done is using these two triangles worked out all of these special values. So I know what cosine is, sine and tan at pi over 4, pi over 3 and pi over 6. Very important. So as I've said a few times, I can't stress enough, like, take the time to internalize how I've got these. Don't try and memorize what's in the box. There's no point. Understand how I've got to it, because in a pinch, in an exam, you'll be far more likely to remember, oh yeah, I need to do something with an equilateral triangle, than what's the exact format of some arbitrary table that I memorized 4 months ago. Okay, so you should definitely take these to heart. When I'm doing problems like this, and I'm dealing with things like cos of pi over 3, cos of pi over 6 or whatever, I have to go through the process of thinking about this equilateral triangle. I don't know it immediately, right? So I don't instantly know that, okay, cos pi over 3 is the following. It's a half. All right? I haven't committed that to memory really, right? And I'm really telling the truth there, but I do know how to calculate it. So I always kind of draw a little equilateral triangle and take the time to kind of think it through exactly what's going on. So take the time to do this yourself for sure, because it's a really useful thing to do, and it will make remembering these values much more straightforward. Okay, some other special stuff. I could have talked about this way earlier, but it's worth doing it now. When we're talking about the signs of sine, cos, and tangent, it's very simple. So the sine of cosine, sine, and tangent. So let's just think about the sine. So when I say sine, I mean sine as the output. Is it positive or negative? It's that simple. So again, it's worth going through this carefully at least once to make sure you understand why these are true. This again is something a lot of people just memorize without understanding, and that's not how you should approach it. Anything, right? Absolutely not. Certainly not at the university level. So same old, x, y. Unit circle, 1 minus 1, 1 minus 1. I have an angle theta. I'm winding around. depending on which direction or if you're positive or negative, but here I'm assuming theta is positive. And then my position is, by definition, cos of theta, sine of theta. And let's remember that the slope, it's a very beautiful fact, the slope is equal to tan of theta. A really nice way to interpret the slope geometrically. So from this, we can read off so much, so much. So let's write down just a quadrant diagram, shall we? So a quadrant diagram. So in the first quadrant, so when theta is between 0 and pi over 2, everything's positive, right? The x-coordinate and y-coordinates are positive. So cos is positive, sine is positive. What about tan? Well, the slope is positive too. Positive over positive is positive, so tan is positive. What about when I get over here? Well, over here, the x-coordinate becomes negative, but the y-coordinate is still positive, and the slope becomes negative. So we have the x-coordinate is negative, the sine coordinate is positive, and of course the slope is negative. And that's obvious because plus divided by minus is minus. By the time I get down to here, what's going on? Well, now both the x and y are negative. So here cos, I'll do first, is negative, sine is negative, but then, very nice, the slope becomes positive again. So if the slope is positive, that means tan is positive. Of course, that's because minus divided by minus is equal to plus. So finally, on the other side, the x becomes positive. Now the y is negative, and of course the slope is negative. So this is kind of the final case. This is cosine is positive, sine is negative because it's the y-coordinate, and of course the slope becomes negative. So useful stuff to understand. Very nice. So again, don't memorize that. Absolutely not. Understand why it's true. So I couldn't have written down the right-hand side here cold without having at the very least, thinking through this unit circle definition.